All right, so hello and welcome everyone to week three of interactive live sessions for the course on computational fluid dynamics for incompressible flows. This course is being offered by NPTEL and it's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm the TA for this course. And like every other week, we shall be solving some problems together and discussing anything and everything related to the course. Now, first of all, I would like to apologize for two things. One is I was unable to attend this session this Tuesday, so we have postponed it to this Saturday. But next week onwards, we will have our regular timings, Tuesdays from 6 to 8. And the second thing is, as you can already hear, my voice is a bit broken. I've got a sore throat, so sorry about that. Now, without any further ado, let's dive into the questions. So we have question number one for today's session. And I'd like to remind you that the whole discussion on week three started off with uh, introducing us to the finite difference method and how it works. So, uh, in order to approximate derivatives uh, into a discretized form, we use this finite difference method, and there are different schemes of that. So, this question relates to a few of those schemes and the discretized form of nothing but dou f dou x. So, uh, so here all these forms are forms of nothing but dou f dou x. How to discretize dou f dou x using forward difference approximation, using backward difference approximation, or using central difference approximation. And we have three mathematical forms over here. Fi plus 1 minus Fi minus 1 by 2 delta x. And so let's draw the template ones. So let's say we're trying to figure out this dou f dou x at this point. Let's call it point I. And we have two neighboring points around it. Let's call them point I plus 1 and I minus 1. And the physical separation between these points, the distance between these points, is uniform. It's delta x over here, delta x over here as well. So if we try to approximate dou f dou x, what would it be? Okay, very good. So we have one response in favor of option D. Let's see what others have to say. So the values of, okay, we've got another response in favor of option D. So let me just break down this problem in a bit more detail as well. So at I, the value of f is f of I. Over here, it's fi plus 1. And at I minus 1, it's fi minus 1. So let's do this. So in what happens in forward difference approximation is that while computing the derivative at a certain point, we consider other points which are forward to that point. So let's say if I is our reference point, so we will consider all points which are greater than I. So I plus 1, I plus 2, I plus 3, depending on what order derivative and what order accuracy you are considering, but it will be I or more. So in forward difference approximation for dou f dou x, we have to consider f of I plus 1 and f of I. Will take the difference between them and just simply divide them by delta x. That's the forward difference approximation. So this matches with 2. So A matches with 2. And what happens in backward difference approximation is simply the opposite. So we will go backwards. If we are considering fi, then we have to go towards fi minus 1, I minus 2, I minus 3, and so on, depending on the number of points that we need. So this one will be fi minus fi minus 1 divided by delta x. So this matches with option 3. So B should match with 3. And that leaves us with central difference being 1, But let's go through that once again. So what happens in central difference is that we leave out the point in consideration and consider two different points, one forward to it, one backward to it. And the only difference between the forward and backward strategies with central is that the uh, total spatial difference between I plus 1 and I minus 1 is twice of delta x. So the form would be fi plus 1 minus fi minus 1 divided by 2 delta x. And that matches with 1 as we can see. So A2, B3, C1 should be the correct answer. Let's take a look, and it is indeed the correct answer. So any questions on this? This is a very fundamental aspect of getting into finite difference method. So if you have any questions, just shoot away. Any questions? Any remarks? Any thoughts? So all we are basically trying to achieve here is that we're converting a continuous function, dou f dou x, into discrete numbers so that we can use a computer later on to solve them. That's all. ट्रंकेशन एरर का ऑर्डर क्या बताता है हमें? ट्रंकेशन एरर का सॉरी ट्रंकेशन एरर का ऑर्डर. Yeah, so what truncation error basically tells us is how accurate your differencing scheme is. So for central difference, let's say the truncation error is second order in this case, and for these two, the forward difference and backward difference, that order would be order one. So basically, uh, if I take a grade of size delta x, then the uh, greatest uh, error that I can introduce into the system will be order of that. And for second order, that will be a bit lower. And remember, this delta x is usually small values, less than 1. So if the order is higher, that means the error will go down. So it's always better to try to incorporate schemes which have a higher order of truncation error. Right? Okay. So, all right. So let's move on. We have question number 2, which relates to the Lax equivalence theorem. Uh, it's asking us to choose the statement which correctly describes this theorem. So there are three statements A, B, and C, and option D just says that none of the above is true. So options A, B, and C are so on. Option A says that if a solution scheme is convergent and stable, so these are all important keywords here. So if a solution scheme is convergent and stable, then it will be consistent. That's what the statement is. Then statement B says that if a solution scheme is stable and consistent, then it will be convergent. And statement C says that if a solution scheme is convergent and consistent, then it will be stable. So basically, the main structure of these statements is that if you satisfy two criteria, then a third criteria will be true. And those criterias are so on, stability, convergence, and consistency. So you just have to put them where they are. And uh, that should correctly describe the Lax equivalence theorem. Okay, we have a response in favor of option B. And we have another response in favor of option B. So let's take a look at the solution. And it is indeed option B. Well done. So the thing is, the let's discuss these terms first. So first one should be consistency, and the next one should be stability and convergence finally. So what does consistency mean? Consistency means that let's say I have given you a discretized form of a difference. So let's consider the example in the previous slide. So we had dou f dou x, and let's consider central difference scheme. So we had this fi minus 1 I plus 1 minus fi minus 1 divided by 2 delta x. So one scheme is said to be consistent if and only if uh, this whole thing with under the limit. So I'll just remove this. So this will be true only if this whole thing under the limit of delta x tends to 0 is actually equal to the original partial differential terms. I'm just considering one term over here. You'll have to consider the whole partial differential equation in a real case. So if this is true, then only it will be called as consistent. Now, this might seem trivial that we are starting from a partial differential equation and we are discretizing it. So the discretized form under the limit that those delta x and delta t is going to 0 should again go back to the same partial differential equation. But no, there are certain cases where people introduce weird discretization schemes. We will learn a few of them later on uh, in order to make the whole thing stable. But the drawback there is that it might become inconsistent. That even if we put the limits that delta x, delta t goes to 0, the whole equation would then not go back to the original partial differential equation. So this is one important criteria of consistency. Then stability, we will learn more when we learn about error dynamics and error equations. For now, just take this into try to understand this, that there will definitely be some errors in the system. Now, uh, while you're trying to solve, so let's just consider this a black box. This is nothing but your code, your solver code. That should not blow up the error. Like if we consider number of iterations, let's call number of iterations n. With each iteration, the error should not go up. Rather, if we can ensure that it goes down, then better. So this is what differentiates between uh, an unstable and a stable scheme. So schemes in which errors go down with more and more iterations, those are called stable schemes. And if it goes up, then it's an unstable scheme, in which case you won't get the correct solution whatsoever because your errors will become greater than the actual quantities that you're trying to solve. So let's say if you're trying to solve for u velocity and you have some error u along with it, and if it blows up like this, then your uh, error u will be greater than the actual value that you're trying to solve for. So this whole thing would go out of whack anyway, so it won't make any sense. So now coming back to the third thing, the convergence. So the textbook definition of convergence is that the solution of the finite difference equation that we're trying to solve with more and more iterations, if it approaches the exact solution of the PDE, the numerical solution of the difference equations, if it approaches the exact solution of the PDE, of course, with delta x and delta t approaching 0, then this whole scheme is called a convergent scheme. Otherwise, it's not. So, and what Lack's theorem tells us, it's a very powerful thing that if you can ensure consistency, that you can do by simply looking at the equations. And if you can ensure stability, That you can do by, uh, you know, picking proper solution schemes. If you do these two, then you can guarantee that the uh, scheme that you have chosen will definitely converge. The solution that you get from that scheme will be convergent. So this is actually pretty strong. So Lax equivalence theorem has been proved mathematically for linear PDEs. There is a proof for this. You can go on the internet and find it out. If you need help, you can ask me. I'll help you find it. So there's a mathematical proof for linear PDEs which are marching in time. For nonlinear or higher order PDEs, I don't think there's a mathematical proof, but however, this theorem holds true for all cases. So it's a really strong theorem and useful as well. Anyway, so that's all about Lax equivalence theorem. Any questions on this? In the exam, the question will be like the ones you solve or like the assignments. They are similar, right? The questions which I ask and the ones that are there in the assignments. So yeah, in the final exam, they will be like this. The topics covered will definitely be the same. The format might be a little bit different. I cannot guarantee that it will be all, MCQs like the ones we solve here and in the assignment. There might be some numerical type questions and so on. I don't know the exact exam format of NPTEL, but yeah. But the topics and things that we emphasize on, those will be the same. Anything else? Any other questions, thoughts? Okay. So if not, we will move along. We'll move on to question number three now. So we first of all define some variables here. So P, F, N, R, and D. These are, uh, so let's say P is the exact solution of PD, the partial differential equation. F is the exact solution of the finite difference equation, FDE. And N is the numerical solution of FDE from a real computer with finite accuracy. Now, this is all just caveat for, uh, you know, it just has some round of error along with it. So this has a round of error. That's all. So all real computers, as we know, they have some finite accuracy. Like there will be a finite number of digits that it can go up to. Usually, it's this number is also pretty high up for the 64-bit machines, but then again, it's limited. It's not unlimited. So there will be definitely some round of error, and that round of error is being denoted by R over here, and D is the discretization error. Now you have to pick the incorrect option from the four cases over here. So there are four mathematical cases given here. So mathematical equations rather. So you have to find out which of these equations are correct and which one is incorrect. So there is one incorrect option hidden within three correct options over here. Take your time, try to go through each equation and try to see if it's correct or not. There's no hurry, take your time. Okay, we'll see. So someone says that it should be option A. Let's see what others have to say. You have to pick the incorrect option, by the way, not the correct one. There could be that there are actually uh, three correct options and one incorrect option. So someone else says that it should be option D. Let's hear from others. Okay, we have a response in favor of option C now. Only B is left. Okay, let's take a look at the solution and we will go through how to do this. So the correct option is actually option D. And how do we get there? So the first thing is uh, these two, exact solution of FD and numerical solution of FD. So both are solutions of FD. The only difference is that this one, N, has round of error in it. So N is actually the exact solution plus some round of error R. So from here you will get R equal to N minus F. So option A is correct. This statement as a mathematical statement, it's not false, it's true. Now, the discretization error is defined as the difference between P and F. So between the exact solution of PD and exact solution of FDE. So this is like telling that if I had a computer with infinite accuracy, then uh, whatever solution I got, that would still be different from the exact solution of PD, and that difference will be this discretization error, right? So D is P minus F. Now we can play around with these two equations. So let's just separate out P over here. So P would be F plus D, right? From here. And we have this equation as well, R equal to N plus F. So C and D, let's try them out. So C says R plus P. So R plus P should give me N minus F from this equation and plus F plus D from this equation. So these two F's will cancel out and I should get N plus D, which is exactly what statement C says. So this one is true as well. Now let's take the difference as statement D says. So if I take R minus P, then I'll get N minus F minus D. So this would result in N minus 2F minus D, which is not D minus N. So this is the only incorrect statement over here. And since we had to choose the incorrect statement, this option D would have been the correct answer. Any questions related to this? Now, understanding the math is pretty simple. This is just algebra that I did here. But uh, what you should focus on over here is what the definitions of these errors are. What is a round of error? What is a discretization error? These things are important. So, any questions on this? All right. If not, we will move along. We'll move on to question number 4 now, which is asking us what is the order of accuracy for forward difference approximation of a second order derivative. So dou 2 f dou x2. And I'm using forward difference approximation for this. So if I do that, what will be the order of accuracy of that? Will it be option A 2? Will it be option B 1? Will it be option C 0? Or will it be option D insufficient data? Okay, we have one response in favor of option A. That is 2. Let's see what others have to say. Okay, let's take a look at the solution. It's actually option D, insufficient data, because I haven't told you the number of points that you can use. So let's start from here. Since we are using forward difference approximation, I'll start from I and I'll take points I plus 1, I plus 2, I plus 3, and so on. Right. Now, uh, since it's a second order derivative, I'll need at least 3 points. So if I take 3 points, I plus 1, and I plus 2, then I might get some order of accuracy. If I take 4 points, I plus 2, I plus 1, I plus 2, I plus 3, then I may get, generally we get one higher order of accuracy if we use more number of points. So if I include more points, then the order of accuracy will be higher. So if I don't tell you the number of points that you're allowed to use, you can't really tell that what will be the order of accuracy then. So since this question did not have that data, the correct option you should have picked should have been insufficient data, right? So let's take one simple case in which we can take a look at this. So let's say dou f dou x, for example, and we are using forward difference approximation. So if I use I and I plus 1, so I'll just write this. So if I use just 2 points, I plus 1 minus I by delta x, this is order 1, right? But if I use 3 points, so there is a some functional form of it. I don't remember the numbers, but you'll get something sort of this. Some alpha into fi plus 2, beta into fi plus 1, and gamma into fi divided by, again, some delta x should be there. Some prefactor, okay, that prefactor might be introduced into this alpha, beta, gamma. These are just numbers. Let's not focus there. Uh, this will be order of delta x square, so it will be a second order. I can add 4 points and get third order and so on. So could I make myself clear with this whole thing? Any questions on this? The main point over here is that the number of points determines the order of accuracy. If you want a higher order of accuracy, you can choose a scheme which uses more points. Then your math will be messy. That's the trade-off you have to make for a higher order of accuracy. Anyway, okay, so let's move along. We'll move on to question number 5 now, which is asking us what is the main purpose of using a non-uniform grid? Is it to option A to resolve sharp gradients, option B to get higher order of accuracy, option C, to ensure convergence, or option D, all of the above. The non-uniform grid means just this. So we have been discussing and mostly been sticking to uniform grids where all points are equidistant, no matter which two set of adjacent points that you consider. All will be delta x, delta x, delta x like this. But in non-uniform grids, you can have, uh, you know, uh, a few more grid points over here close by, and in some other place it might be spaced far apart. That sort of a thing. Okay, so we have a response in favor of option B. Let's take a look at the solution. It's actually option A, to resolve sharp gradients. So let's take an example. Let's say the boundary layer example that we saw in class. So what happens in boundary layer is that we have a flat plate like this, and some flow comes and hits the wall and slows down, and near the wall, a very thin layer forms, which is a boundary layer. And within that boundary layer, there's a huge sharp gradient of velocity. So it's zero at the wall, and within a very short distance, this could be low. So let's say this length is in meters, and this boundary layer thickness could be in millimeters. So 0.001 meter maybe. So within this short distance, your velocity literally goes from 0 to 99% of whatever the maximum is. And it remains the same for the most other part. So this is what the velocity profile looks like. So it's mostly uniform everywhere else. And within the thin boundary layer, there's a very sharp gradient. So capturing these things are very difficult. So uh, let's forget fluid mechanics for a moment and think about some number. Let's say some f that you're trying to solve. And let's say you know the exact solution. Let's say the exact solution is like this. Okay. Now, let's say you took grid points which are spaced like this. So you would be able to sample this point, and this point. So what would your numerical solution look like? So you will have this point over here. So you'll have this one, you'll have this one as well, and you'll have this one. So to you, the curve might be looking like this, right? So is there any similarity between these two? You're obviously missing some, drama that's going on here. There's a sharp dip here, there's a dip over here, and so on. So in order to resolve those, we need to have a very fine grid in this region. And in this region, it's not so important because that's mostly flat over there. So in regions of sharp gradients, where, you know, we are considering F here, so uh, wherever there's a lot of ups and downs going on, there dou F dou X would be pretty significant. So that's what a gradient is, right? So wherever there's a sharp gradient, we need to resolve that with very fine grids. We need to probe into what's going on in between. We can't just leave them out. So that will give you an erroneous solution like this. Otherwise, the other things like to get an higher order of accuracy, it doesn't really make sense. You have to make the whole grid finer then. Just making it non-uniform doesn't help you. And to ensure convergence, convergence is not that simple. There are many other things involved. So once again, non-uniform grid doesn't directly help you to get convergence. Indirectly, it might. But the main uh, purpose of using non-uniform grid is to focus on the sharp gradients in a domain and keep the computational cost pretty low by not using the same fine grid in spaces where the gradients are not so sharp. So let's say in this flat region, it doesn't really make sense to have a very fine grid over there. We would be driving our computational cost high up without any uh, you know sizable returns. So the return on investment would be quite low over there. Right. So that's all about non-uniform grids. Any questions on this? Why we use alpha phi plus beta phi gamma phi minus 1 to find finite difference approximation in uniform grid. Uh, yeah, those alpha beta gammas are just placeholders. So let me show you this. One sec. So those are just numbers. So let's say I'm trying to find dou f dou x, and I say that alpha fi plus 1, beta fi plus gamma fi minus 1. Thing is, I'm just fixing that I will use 3 points, and there will be some coefficient alpha, beta, gamma associated with the values at those 3 points. Now, to find the exact numbers, we need to do some math. So for that, we can use the Taylor series expansion and so on. Directly, why cannot we write the equation? So yeah, if you can write, then directly why we cannot write the equation as that of central difference scheme forward and backward. Yeah, the thing is that, mm, sorry. Yeah. So the thing is, if you know these values, so for central difference, let's say if I had used alpha f I plus 1, so exactly for this case, if I am using central difference scheme, then I know that alpha is equal to 1 by delta x, 1 by 2 delta x, I think. Beta will be minus 1 by 2 delta x. And gamma would be, sorry, beta will be 0, this will be gamma, and beta will be 0. So I could intuitively find this because I know the simple form fi plus 1 minus fi minus 1 divided by 2 delta x. I could simply say that the 1 by 2 delta x and so on. These are just coefficients, yeah, nothing else. Now, in case when we don't know these numbers, 1, minus 1, and so on, then we need to find these, right? So these variables just become the placeholders until we know the exact numbers. So let's say if I added one more point over here, uh, you know, like something like delta f I plus 2, let's say. And instead of central difference equation, I use forward difference using these 4 points. In that case, we need to use Taylor expansion to, expand out these numbers fi plus 1, fi minus 1, fi plus 2 in terms of fi and the derivatives. And then we need to solve for these numbers and find out what these are. So it might give you something like, so this is not a true example, but it might give you something like alpha equal to 1. Uh, Forget delta x for a moment. So let's say, let's take delta x below over here. So let's say alpha equal to 1, beta equal to minus 2, gamma equal to minus 2, and delta equal to minus 1, something like this, or beta equal to plus 2. Anyway, something like this. Then you know that the discretized form would be fi plus 1 plus 2 fi minus 2 fi minus 1 and minus fi plus 2. This is no real equation, I just made this up, but you know, this will definitely not be correct, but I'm just telling you that this is the process. Alpha, beta, gamma as such have no value over here. We just have to find them. Does that answer your question? Okay, we have another one. Let's see. Which boundary condition is more accurate for 5-point formula? slash governing equation. Which boundary condition is more accurate? Boundary condition is more accurate. Boundary condition would depend on the system, right? So let's say if I have something like a wall, I have to use a wall boundary condition, which is a no slip wall boundary condition. Let's say u equal to 0, v equal to 0, that sort of a thing. And if I have an inlet and I specify u over there, then that's a Dirichlet type boundary condition, that sort of a thing. I'm not sure I understood your question correctly. So these are what boundary conditions are for grid solution. Which boundary condition is more accurate for? Uh, oh, okay. So if I understand you correctly, so it could be that, um, the thing is, let's say if I have a domain like this, for the inner points, I can use central difference scheme, right? Central difference over here. But for these endpoints, I have to use either forward difference because there is no point over here. There are missing points on either side. So here I have to use backward differentiation. So these schemes are better suited for boundaries. Is that what you're asking? Or something else? So for points at the boundaries, either forward difference or backward difference is better. And for points in between, I can use central difference schemes. Does that answer your question, or was I completely off the tangent? When we calculate phi n, then I'm still not sure what you're asking. Can you give an example, like what you're talking about? Don't just leave it, ask it. Come on, you can unmute and ask as well. Let's have a discussion. This is for your questions are more important than mine over here. Sir, please explain another method of non. Okay, we will come to that. But yeah, yeah,
हेलो।
Tushar. Hi. Yes.
भैया जैसे कि हम गवर्निंग
Hmm.
इक्वेशन जब सॉल्व करते हैं ना,
Hmm.
तो उसमें हम ग्रिड बनाते हैं, पहले ग्रिड से ग्रिड कंसीडर करते हैं।
Hmm.
तो
Hmm.
उस ग्रिड का सॉल्यूशन निकालते वक़्त हम बाउंड्री कंडीशंस लगाते हैं कई सारी।
Hmm. Hmm. Hmm.
तो जब मैं पढ़ रहा था तो सर ने बताया था, मतलब सर बता रहे थे हर बाउंड्री कंडीशन से सॉल्यूशन निकालने की कोशिश कर रहे थे।
अच्छा।
तो मैं वही पूछ रहा था सर, कौन सी बाउंड्री कंडीशन इज़ मोर एक्यूरेट?
ये बाउंड्री कंडीशन तो इस तरह का होता है ना कि आइदर डिरिचले बाउंड्री कंडीशन और नॉयमैन बाउंड्री कंडीशन, वो तो प्रॉब्लम के ऊपर डिपेंड करेगा कि वहाँ पे इनलेट है, उस बाउंड्री, व्हाट डज दैट बाउंड्री बिहेव लाइक, डज दैट इज दैट बाउंड्री अ वॉल और इज इट एन इनलेट? Depending on that, the boundary condition would be determined. We don't have a
ओके,
free choice of boundary condition over there.
मतलब सर हर सरफेस के लिए हम अलग बाउंड्री कंडीशंस यूज़ करते हैं।
हाँ,
ओके,
मतलब
ओके।
if it's a like a non-slip wall, तो वहाँ पे u equal to 0 होगा. There are some surfaces which allow slip over it, like the fluid can slip, it can have some finite velocity. In that case, there's a slip wall boundary condition. There could be, other various types of boundary conditions depending on the surface.
ओके, आई गॉट इट।
Okay. Okay, cool. So the other thing is the non-uniform grid. Yeah. So this has become a bit messed up. I'll go to back to my previous slide. Yeah, I have some space over here. So that's nothing, just uh, sorry. So one way in which non-uniform grids are made is that you specify that there's a certain change factor between or expansion factor between the two spacings. So let's say if the first one is delta x, then the next one would be r delta x, and the next one would be r square delta x, and so on. And r is usually small numbers like 1 between 1 and 1.2. So 1 means uniform grid, and it's if it's a little bit more, then the grid would expand. And okay, sorry, so r could be zero point 0.8 as well. So and if r is less than 1, then that means that the grids will shrink as we go along. So this is one way of doing this. So in this case, the grids will expand slowly if r is positive. Now, in certain cases, we don't just want continuous expansion. We want expansion up to a certain case, and then we want again it to come back to smaller and smaller, and finally we should get delta x back. Sorry. So there was some mathematical form which was derived in the lecture. I'll try to get those slides back up here. Hold on a sec. You guys can see my screen, right? Taylor series expression. No, no, this is not that. This is different. So let's say lecture notes. Hmm. Yeah, this is the one. So over here, if you look at the grid first, so you can see that near the walls, the grid size is pretty small, and near the central region, the grid sizes are pretty big. And again, near the wall, it becomes smaller. So that is achieved in this way. So uh, we first define a delta eta 1, which is uh, sorry, which is like the change factor. So not the change factor. So this is sort of delta x, and up to L by 2, we want it to expand. And after L
Sir,
by 2,
I can't see the I can't see the new screen that you are
oh,
trying to present.
okay, sorry. Hmm. Is it visible now?
Yes, sir.
Okay. Sorry about that. Yeah. So over here, so this is the thing. So we want smaller grid sizes near the walls. we will allow it to expand in the center, and they will contract and become smaller again near the walls, because near the walls are the boundary layer regions where uh, there are sharp gradients usually, and we want to resolve them by finer grid size. So over here, this delta eta is basically like delta x. So, and the change factor is r. So delta eta 1, then the next spacing would be r into delta eta 1, and so on. And we want these numbers to expand up until L by 2, that is the center of the domain. And then after L by 2, we want it to contract back again. So, uh, and cal is equal to ni minus 1 by 2. So yeah, so if the total number of points is ni, uh, then the point up until which it increases, that is L by 2, would be this n cal, that is the uh, number of grid point up until which expansion occurs, and after that there will be contraction. So if we say that this any delta eta I is this L by 2 by A, and A is defined in this manner where r power n cal minus 1 divided by r minus 1, and also we have plus r power n cal minus 1 by 2. So what this equation does is that, so here we should have some dependence on the point, right? So
सर ये
uh,
इक्वेशन जो है वो जो
uh,
ऊपर फिगर बना है
uh,
उसके द्वारा ड्राइव ड्राइव करी गई है या फिर क्या यूज किया है मतलब, या ये पहले से ही मतलब ऐसे एक इक्वेशन अपन ने बना दी है वो उसके लिए
no, no,
मतलब ये।
no, there's a proper mathematical derivation of it. It may not have been uh, discussed in the lecture, but we can understand from the mathematical form of the equation. So the only thing is there should be some dependence on uh, this the point where we are residing at, like having some I dependence over here. Give me a second, I'm trying to figure this out. Current cal minus 1. This one's fine, but I think there should be an I somewhere in this equation, meaning that the value of A should change depending on which point I'm at. Mm, okay, I'll look into this in more detail and we will discuss this the next day, okay? I'm sorry, I can't really figure it
ओके
out
सर।
right now.
सर
Okay?
लेक्चर में जो वीडियो होती है मतलब उसमें
Hmm.
वो कंटिन्यूअस मतलब पूरा थोड़ा थोड़ा बेसिक सा नहीं बताते हैं, मतलब वो ऊपर ऊपर से कराते जाते हैं, सॉल्व कराते जाते हैं, तो समझ में नहीं
Because
आता सर।
the see, this whole subject involves a lot of math, right? So uh, starting from basics and deriving everything will make the course even longer. So there are certain things which are done that way. So you have to go back, like take responsibility of those things and go back and figure them out yourself. So we can't really do anything about that. Now, of course, there are some important things which we need to know, but uh, deriving everything from scratch won't be possible. But yes, this particular problem, I will, do some homework on it, and we will discuss this next Tuesday. Right now, let's move on.
सर उसका जो
Uh,
ग्राफ था आपने बताया था
hmm,
कि मतलब जीरो से लेके जीरो
hmm,
पॉइंट टू फाइव तक मतलब बहुत फाइनल मैच है, फिर
hmm,
उसके बाद ज्यादा फाइन नहीं है।
hmm,
तो ये क्या जी सॉलिड बाउंड्री मतलब ये तो सॉलिड मॉडल सॉलिड कुछ रहता है नहीं, ये सॉलिड रीजन मतलब तो हम सॉलिड रीजन पे फाइनल मैश मिलती है क्या, जिसका स्मॉलर डेल्टा एक्स रहता है?
हाँ मतलब सॉलिड सरफेस के पास we have to take smaller grids because wherever there is a solid surface and like some flow near that, there is a chance of boundary layer formation. Or boundary layer formation leads to this high flow gradients, and to resolve high gradients, we need, you know, very fine mesh. So we need to do this, like the you get the point, right?
ओके सर।
Mm. So we design this non-uniform grid, we design this fine grid so that we can resolve the actual behavior better.
ओके।
All right. So I will, we will revisit that problem this next Tuesday. We will in fact start with that. And for now, let's move on. If you have any other questions, please feel free to ask. All right. So let's move on to question number 6. It's asking us this that as the number of grid points increases, what happens? So option A says that the round of error decreases. Option B says that truncation error increases. Option C says both A and B. And option D says none of the above. So for the same case, if I have, let's say, only 3 points, and for the same case I take 300 points and then try to solve it. So in that case, what will happen to these two errors, the round off error and the truncation error? Does it go up? Does it go down? What happens? Okay, we have one response in favor of option A, that round of error decreases if I increase the number of grid points. Anything else? So the main point over here is that the length of the domain is the same. I had used 3 points earlier and let's say 30 points later. So if I increase the number of grid points, the delta x over here, and there is, let's call it delta x prime over here. Delta x prime is obviously becomes smaller than delta x, right? So there are two different things happening over here. So we got another response. Let's see. Okay, option A again. Good. So let's take a look at the solution. It's actually option D, none of the above, because both A and B are incorrect. Let's discuss that. So round of error actually increases because since the number of points, number of data points has increased. So let's say for the first case where you had only 3 points, I had to solve for F1, F2, F3, store them in a computer code and solve it, right? So the round of error I was in introducing into this whole system was only thrice because there are only three variables that I'm solving for. Now, once it becomes 30, F30, I'm introducing this round of error 30 times because there are 30 different variables which are stored in a computer, and all of them have some round of error associated with it because the memory of the computer is limited. Now, the not the memory, the accuracy of the computer. Now, uh, which is why in many cases when we increase the number of grid points, the round of error that actually increases with number of grid points increasing. I'll call that G. So with G increasing, the round of error increases. Sometimes proportionately increases, sometimes not so much. But anyway, so there's another thing. So the truncation error. So the truncation error, if you remember, depends on, the order of accuracy of the scheme that you're using, but it's of the form delta x power n, right? If it's second order, then power 2. If it's third order, then power 3, but whatever, it depends on delta x. Now, as you can see here that as we increase the number of grid points, the grid spacing size, the delta x, that becomes smaller. So if delta x becomes smaller, the truncation error becomes smaller, right? So truncation error actually decreases if I increase the number of grid points. So it's the balance between these two which dictates whether increasing grid points will make my solution more accurate or not. In most cases, more often than not, the decrease in truncation error dominates in the decrease in truncation error dominates the increase in round of error, but not always. You have to be careful about that. So both of these statements, A and B, are true. And that's why option D would have been the correct answer. Right. Any questions on this? Was this whole concept clear? Why round of error increases and truncation error decreases with increase in number of grid points?
Yes, sir, clear.
Okay, good. Any questions or doubts related to this? If not, we will move along. We'll move on to question number 7 now. So we have a fourth order accurate scheme. My God. So this is fourth order accurate. So we have delta x power 4. And this is basically f double prime, the double derivative of x. So as I said, you can increase the number of points and get a higher order of accuracy. So we are using 5 points over here. Uh, so on top of fx, we're using fx plus 2h plus fx plus h and x minus h and x minus 2h as well. Here, just to make you familiar with the terminology, h is like delta x, and uh, we have been talking about fi for so long. We're just replacing it with f of x. These are just same things written in a different manner. So you have to pick the correct values for A, B, C, D, and E. I'm not asking you to solve it, but there's a neat little pattern which is followed by these different schemes. You have to use that pattern to crack the correct solution here. You can always try to solve for this. I'm sure there are derivations of this sort of a thing, and that will be a good practice, but it will be a waste of time as well. If only finding out the numbers from a given set of solutions is the thing. If you didn't have these options, then obviously you would have had to use Taylor's expansion and then go through it. So I'm not able to solve this as this type of question is present in the assignment too, so please solve it. Okay, so I'll be helping you with your assignment, right? In the assignment, same question was there. If it was, then I'm not allowed to use the same problem here.
Sir, in my assignment 3, but the date for assignment 3 is on the last date was 12th
Okay.
of February.
Cool. Then we can discuss freely. Then it's legal to discuss. Otherwise, it would have been illegal. Anyway, take a shot. What do you think it could be?
सर इसमें अप्रोच क्या लगानी है वो चीज समझ नहीं आई थी, मतलब
Okay.
कैसे मतलब वैल्यूज डालते हैं।
Okay, so there's a neat little pattern which this sort of discretizations usually follow. So let's take a look at the basic ones. Let's say for dou f dou x using central difference scheme and so on. We have seen that it's usually fi plus 1 minus fi minus 1 by something 2 delta x. So here the coefficients are plus 1 and minus 1, right? So plus 1 minus 1 equals 0, the coefficients. Then let's say dou f dou x using 3 points central difference. The form is like this: fi plus 1 minus 2 fi plus fi minus 1 divided by 2 delta x. So here also look at the coefficients. We have 1, we have minus 2, and we have plus 1. So if we consider the sum of the coefficients, then we'll have 1 minus 2 plus 1 equal to 0. So there is no mathematical proof for it, but usually most such discretizations follow the same pattern where the sum of the coefficients would turn out to be 0. So in case if you're given the some set of options to pick from, then you have to look at the differences. Yeah, same, but difference. So you have to find out the sum of them and see if the sum adds up to 0.
ओके सर।
So for the first one, minus 1 plus 16 minus 30 plus 16 minus 1. So 16 plus 16 is 32, and minus 30 minus 1 again 32. So this one adds up to 0. Then this one, it doesn't. Right. What is it? 32 plus 2, 34 minus 30. So 4. Then this one is 30, 62 minus 2. So 60. And this one would be minus 32 minus 34. So minus 4. So it's only option A that adds up to 0. So if you take out the correct solution, it is actually option A. And if you use Taylor series expansion and everything and put in a lot of hard work, sweat and tears and everything, then also you will find ultimately that this will boil down to minus f I plus 2 plus 16 f I plus 1 minus 30 f I plus 16 f I minus 1 minus f I minus 2 and divided by 12 its squared, or the way we have been writing delta x squared. So this is verified. You can go find out anywhere. You can ask ChatGPT what is the fourth order accurate scheme for double derivative of f, and I'm sure this is what you'll get.
ओके सर।
But yeah, the main trick over here is that it should add up to 0. And it is hidden trial method sometime, of course. Jai Mata Di. Okay, so rolling to question 8 right now. What is the order of accuracy for the mixed derivative? So we have this mixed derivative over here, dou to f, dou x, dou y, using central difference technique, using the points as shown in figure. So I have drawn a figure over here earlier. So I want to find the value of dou to f, sorry, dou to f, dou x, dou y at this point, I comma j. So using central difference technique. So in this case, what will be the order of accuracy of that? Will it be 1, 2, or 3, or none of the above? And the catch over here is that I can only use the points that are shown in the figure. So there are 9 points shown in the figure, right? I plus j is the original point. I can use 3 to the left of it, 3 to the right of it, 3 above, and 3 below.
सर एक क्वेश्चन था सर, जैसे
Hmm.
आपने बताया कि अपन को सॉलिड सरफेस के पास में
Hmm.
फाइनल मैश चाहिए होता है, क्योंकि
Hmm.
वहां पे अगर जो हाई फ्लो ग्रेडियंट्स रहते हैं उनको रिजॉल्व करने के लिए,
Hmm.
तो हाई फ्लो ग्रेडियंट्स जो मिलते हैं तो उसको रिजॉल्व करके अपन को मतलब मिलता क्या है, पीछे का उसका रीजन क्या है, सिग्निफिकेंस मतलब क्या है, वो अपन कर क्यों रहे हैं सॉल्व वो।
Uh, क्योंकि हाँ, the main thing is this. So there is a whole historical reason behind this. So basically, in case of a boundary layer, when the boundary layer theory was first being developed by, you know, this was World War II, during which Ludwig Prandtl and some of his students were working on this. So their main objective, they solved a lot of problems with this, obviously, down the line, but their main objective was to find out what's the gradient over here, the velocity gradient at the wall, the dou u dou y at exactly y equal to 0. So that would determine what would be the stress over here. So the shear stress on the wall would be given by something like, so the Newton's law of viscosity, basically. Dou u dou y at y equal to 0. You have learned this, right?
यस सर।
So this is what determines that in case I have an aircraft uh, uh, wing like this, the shear stress on this wing would depend on this equation that, would depend on this gradient dou u dou y, and that would determine how much power is required in order to fly the aircraft, and that would determine how much fuel I would need to load in an aircraft to, move from one city to the other and, bomb the hell out of it. So that was the
यस
main
सर।
motivation during World War II, which led to a lot of development in this boundary layer theory and all that. But leaving out the historical aspect of it, like that is important, definitely. So, leaving that out, the main point is that we need to find the shear stress on the walls. That becomes very important for, power requirements, for finding out at what rate the wall might get eroded away. That would also depend on the shear stress. So let's say there is a lot of CFD work being done on blood vessels right now. There's a biomedical engineering coming together with fluid mechanics quite a bit to. So the main thing over there is that uh, if there is an aneurysm, so an aneurysm is nothing but, if you have a blood vessel like this and you have a small growth on your arterial wall like this, so the shear stress on this wall would determine the growth of this aneurysm, and this might keep growing and ultimately burst out, leading to hemorrhage and all sorts of bad things to your health. So over there also it's the shear stress that becomes important. So although these are very specific examples, but the main thing is near the wall there is a huge gradient and I want to resolve it so that I can find out the exact things which are happening at the exact vicinity of the wall, because that gives me the shear stress. So this is only fluid mechanics. In case of, if you have convective heat transfer, so then also the convective heat transfer coefficient H would again depend on the dou T dou Y at the wall, the temperature gradient exactly at the wall. So H would determine the total rate of heat transfer that you're trying to achieve. So in that case also, this is what exactly becomes important.
So we are finding these higher gradients to just
Hmm.
find the shear stress.
Hmm.
Okay.
Only the gradient at the wall matters. That's
Okay.
the sad part of this whole story. So you don't need the entire thing in most cases. Like for the entire domain, whatever is going on, you may not need for most cases. It's only the gradient for which, in order to get the gradient, you need to solve the rest of the thing.
Okay, sir.
So it's a lot of effort to find out one little number, but that one little number determines a lot of things. Okay, so coming back to this question. So I have one point at which I need to find the mixed derivative, and I'm using central difference technique. What would be the order of accuracy? Did we get any response in between or no? Okay, go ahead, shoot your shot. What do you think? So I'll give you one hint over here. So in each direction, if you look at, so let's say if in the x direction, be it in the y direction, there are only 2 points that you can access, one in front and one at the back. So given that limitation, what would be your order of accuracy? B. Anyone else? Okay, let's take a look at the solution. And 2 was a good choice because so see, either way, if you're trying to find out the dou x part, you can only have access to I minus 1 and I plus 1. So using central difference, you will get something like this by 2 delta x. This will be second order accurate. If you go in the y-axis also, it will be the same. So I'll show you the exact solution for this. It's pretty simple. So dou 2f, dou x, dou y can be broken down as, dou x of, I'll do the dou f, dou y thing first, right? So dou x of dou f dou y. I'm starting at I comma j, right? So this is my starting point. So I'll split into two. So I'll take this point and this point. So I'll write f I j plus 1 minus f I j minus 1 divided by 2 delta y. This is delta y, by the way, and this is delta x. So then it just becomes another step. So I have, I'll take this 2 delta y outside and I'll do dou x of f I comma j plus 1 minus dou x of f I comma j minus 1. You guys with me so far? So now I'll,
Yes.
yeah. So now I'll one by one do this. So for this point, I comma j plus 1, I'll take this point and this point to find out its dodo x. So this will simply be f I plus 1, j plus 1 minus I minus 1, j plus 1 divided by 2 delta x. And similarly for this point, I will go this way. I'll take this point and find the dodo x at like this. So I'll need I plus 1, j minus 1 minus I minus 1, j minus 1 divided by 2 delta x. Now we have found the solution. We can simplify this and give it a more neat look. So I will take this 2 delta x, delta y outside and just figure out the proper signs for them. So I have I plus 1, j plus 1 minus I minus 1, j plus 1 minus I plus 1, j minus 1 and minus minus plus f I minus 1, j minus 1. That's all. And obviously these are both second order accurate because I took nothing but central difference using 2 points. Any questions on this? Okay, if not, let's move
No,
along.
sir.
Yeah, okay.
सर जितनी बार
Yeah.
हम डिफरेंशिएट करेंगे किसी उसको
Hmm.
सेंटर फंक्शन को तो उतनी बार उसका ऑर्डर बढ़ता चला जाएगा एक्यूरेसी का।
नहीं, ये बढ़ता तो नहीं चला जाएगा वो। लेट्स गो बैक। या सॉरी। So I used central difference scheme on finding out the dou y over here. So यहाँ पे order of accuracy इसका आएगा dou y squared and it remains that क्योंकि I'm not differentiating with respect to y anymore. So then after that, I then perform dodo x on it, and I use a 3 point central difference scheme. So over here it becomes delta x square, and I had delta y square from the first. So we are differentiating only once with respect to x and once with respect to y. If I used, differentiation with respect to x again and again, then that thing might come into the picture, that the order of accuracy might change over there.
मतलब कि सर सेंट्रल डिफरेंस को हम कितनी बार भी डिफरेंशिएट या वो कर लें उसका जो
Hmm.
ऑर्डर ऑफ एक्यूरेसी है वो सेम ही रहेगा मतलब दो।
हाँ, डिपेंड नहीं, जैसे मान लो डो थ्री एफ डो एक्स कर रहे हो, तो if you are doing this dou x of dou 2f dou x squared, let's say, तो तो इसको जितना बारी तुम करते जाओगे उसका ऑर्डर ऑफ एक्यूरेसी एक्चुअली बढ़ता जाएगा. If you are doing this, then again dou x of dou f dou x. So let's say you did this central difference once, then you got something. Then you again use the same central difference technique. Then let's say for the initial one, it would be second order. The For the second time, well, no, it does remain second order. Right? Oh yeah, you're right. It
मतलब सर
won't
ये
change. हाँ हाँ.
फंक्शन का जो
Hmm.
मैक्सिमम ऑर्डर रहेगा उतना ही उसका ऑर्डर ऑफ एक्यूरेसी रहेगा हम ये
Hmm.
कह सकते हैं सर।
Hmm.
ओके ओके।
Yeah, it will remain same. Sorry, you are right. Hmm. Okay. Any other questions? Anyone? Okay, let's move on to question 9. So the question is, which scheme is more suitable for use in boundaries of a solution domain? Is it a forward difference scheme? Is it a backward difference scheme? Is it a central difference scheme? Or is it both A and B? That is, forward and backward. You should be able to tell this because I hinted at the same concept once earlier today. I misunderstood your question. I thought this is what you are talking about. C, central difference scheme. Okay. So the question is, which scheme is more suitable for using boundaries of a solution domain? C again. Okay. Tushar is screaming no in the chat box. So what do you think? Not C? A? Are you sure? So if I have a domain like this is a boundary point, this is also a boundary point. So would forward difference scheme be most suitable for both of them? Okay, okay, let's take a look at the solution. It's actually both A and B. So for the central points where we have points to the, so let's consider I. So where we have points to the left of it, right of it, both ways, then we can use central difference scheme and life is good. But once we go to this boundary points, here if I try to use a central difference scheme, sorry, I might have one point to the right of it, but to the left I don't have any. Similarly for this point, I have this one, but over here it's missing. So in these cases, for the boundaries, we have to use either a forward difference scheme or a backward difference scheme in order to get the same order of accuracy, let's say. So depending on which boundary you're considering, forward and backward means the same, and those are the ones which become more suitable for use in boundaries of a solution domain. That's why option D would have been the correct answer. Any questions on this? Get your confusions cleared. So is the whole concept clear right now? Okay, cool. So now we'll just take a look at the last question of today's session. So this is a match the following type of question where you have to remember what these weird symbols mean. This was discussed in the last lecture of week 3. So these are all shorthand notations. So EN, so E, I will tell you the names of them. So EN is the displacement operator. These are all operators. Delta plus is the difference operator, or rather the forward difference operator. Uh, just call sorry, I'll just call it difference operator. Okay, we already have a solution. C. Okay, man, you're fast. Then delta bar as well as delta, these two are central difference. I was wrong. I should have called this forward difference operator anyway. And these, sorry, and these are central difference operators. Anyway, so all of them mean something. So En just displaces F. So basically, if I say E2 Fi, then I'll simply get Fi plus 2. So it just adds on to it. So in place of 2, if I had n, then I'll get I plus n. So that's this option 2. So A, we already know, should match with 2. Cool. Now the forward difference thing. So delta plus of Fi. That's just forward difference. So it will give you f of I plus 1 minus Fi. Yeah, we have another response in favor of option C. Let's go. So forward difference. I plus 1 minus Fi. So B should match with 3. So far we are good on option C. Then delta bar of Fi gives me the central difference. So that's Fi plus 1 minus Fi minus 1, and that matches with option 1, right? Yeah. And delta squared. So first of all, what does delta mean? Delta is similar to delta bar, but instead of I plus 1 and I minus 1, it gives you uh, I plus half and I minus half. So now if you do it twice, so sorry, Fi. So delta squared Fi It would simply mean that I will again have to apply delta f on I plus half minus delta again on fi minus half. So if I do that, then what will I get? The I plus half. So I plus half will give me I plus 1, and minus half would give me fi. And then this one, I minus half plus half should give me I, and I minus half should give me I minus 1. So if I open the brackets and arrange things properly, so I have 2 minus fi's. 2 fi minus 2 fi, sorry, and minus minus plus fi minus 1. So this gives me 4. So D should correspond to 4. So C1, D4. C does look like the correct answer, and it is. So that's all for today. Thank you.
सर आपने ये डेल ऑफ एफ आई प्लस हाफ का वो कैसे किया? या आपने सेंट्रल डिफरेंस लगाया था यहाँ पे?
हाँ, दोनों ही सेंट्रल डिफरेंस है, मतलब बट देयर इज अ डिफरेंस बिटवीन डेल्टा बार एंड डेल्टा. सो डेल्टा वुड मीन एफ आई प्लस वन माइनस एफ आई माइनस वन, और only delta would mean fi plus half and I minus half. So these are the two differences, and if you use delta squared twice, then you get this form. Does that answer your question, or were you asking something else?
ओके सर.
So these two are very similar, but there's a slight difference between them. Instead of plus 1 minus 1, we have plus half minus half.
ओके सर.
Cool? Okay. Any other questions? If not, so that's all for today. Thank you for joining, and we will meet again this coming Tuesday. Up until then, bye bye. Good night.
गुड नाइट सर.